So now I switch to English. Good morning. This is the 9th lecture of CEE, Controle em Espaço de Estados. And we were speaking about a chapter on controller design, state feedback controller design for linear systems. And we introduced the concept of controllability. And the last thing we did was to show that if you have a linear system with a state realization x not equal to ax plus bu, and then you do a change of coordinates, you can compute the controllability matrix in the new set of coordinates, and you can show in this way that in the new set of coordinates, the realization is still controllable. And then we look at this result the other way around, and we have concluded that suppose that we have two state realizations of the same order, and they are both controllable. Then you can map one state into the other. So you can do a state transformation x equal to t of z. So you can find the t that connects both states. And this t is given by the controllability matrix in the x coordinates times the inverse of the controllability matrix in the z coordinates. Okay? That's a remarkable result. Let me tell you still another thing that we are going to use. Well, this is the result. An example of a state realization which is useful. Useful in what sense? If you have a state realization, then you can do a change of coordinates such that some problem becomes easier to solve. For instance, suppose that you want to solve the state feedback problem. And the state feedback problem, as we are going to see, is find the gains of the state feedback such that the closed loop poles are in desired positions. Now, one thing that you can do is to change your coordinates such that in the new coordinate system, the problem becomes much easier to be solved. Now, solve it in the new coordinate systems and then invert it. We are going to explore this perhaps even today. Now, you can ask, but which coordinate systems are the best ones? I give you one example. So suppose that you have this transfer function. Okay, this is a third order transfer function. Now, one state realization for which you can solve easily the state feedback problem, later we are going to see that, is this controller canonical form. Okay, so you can easily write the state equations considering that the states are the output of these three integrators. Okay, and this A1, A2, A3, B1, B2, B3 are the coefficients of the transfer function. So if you are given a transfer function, you pick up these coefficients, you plug them here, and this block diagram yields this transfer function. Okay, and this is useful. This is going to be useful later. It's the controller canonical form. That's the name. Okay, the name is not much important. And in the controller canonical form, the A, B, and C matrices are these ones that you can see in this slide. And the controllability matrix is the inverse of this matrix here. Okay, so don't get confused of this CC. This is the controllability matrix, and this small c, which is the output matrix. Okay, so this is something that we are going to use later, these results. In particular, if you want to relate any third order system or nth order system which is controllable to the controller canonical form, you can use this transformation given in this way, because this is the inverse of the controllability matrix. Okay, remember that the controllability matrix is this inverted, so the inverse is just this matrix here. Okay, so this is something that we are going to use later. Now, there is another concept, which is the concept of observability for continuous systems. You can have also observability for discrete time systems. And this is related with the capacity to estimate the state given the output. Suppose that you have a system described by x dot equal to ax, so no input, okay? And you have an output which is y equal to cx. I say that the pair AC is completely observable if you observe the output for finite periods of time and you are able to compute initial condition x0. Okay? You might be tempted to say, okay, but if I multiply y by the inverse of c, then I get x. Do you think this is correct?
C might not be invertible.
C, the inverse of C might not even exist, because C, suppose that y is a scalar and x is a vector n, okay? So C is a row. There is not even the inverse, you see? So we are going later to study a technique by which, taking advantage of the model, you can recover x from y. But that's a practical thing. But there is also a theoretical thing, which is to be able to recover the initial state x0. Okay? If you know the initial state x0, then you integrate the equation for x and you get all the x. Okay, but it's not the way that we proceed in practice. Now, the pair AC is observable if this matrix you see here is O matrix, it's the so-called observability matrix, as a rank which is the dimension of x. Okay, so this rank condition applies in any case, even if you have a multidimensional observation. If you only have if y is only of dimension 1, so y is a scalar, then this matrix is invertible, should be invertible. That's the same thing as asking that the rank of the dimension, or the rank of the observability matrix is equal to the dimension. And you can check the observability by just computing the determinant and seeing that this is not 0. Okay? If y has several components, for instance, if I measure position and the velocity, then you will have more rows than columns, and you cannot compute the determinant. Okay? In many cases, we are going to consider just single input, single output systems. So you can just check observability by checking whether the determinant is 0 or not. If it is multivariable, you have to compute the rank. Okay, so as in the controllability case, what happens is that one thing is the definition. So you observe the output for a finite period of time, and you are able to compute the initial state. And the other thing is the criteria that needs a proof. I'm not going to present a proof. Okay? In discrete time, if you have curiosity, the proof of this criterion is in my book, but it's not part of the program. Now, let's do one thing which is quite important. Let's do an interpretation in terms of diagonal systems, not diagonalizable systems, systems that are already in the diagonal form. So suppose that you have state realization in which the A matrix is a diagonal of numbers. Okay? And you can use the same argument that we did in the controllability case to show that the pair lambda C is observable if all these values in the diagonal are different and if all the elements of C are different from 0. Okay, so this is left as an exercise, and I invite you to do it at home after you study the slides. And if you don't succeed, let me know and we can speak by Skype. Okay, now, so consider again the fact that we have a diagonal system, but now we have an input. Okay? And the transfer function is, remember that general formula, no? C Si minus A inverse B. You don't have to remember it by memory. Here you believe in me, but you have to know how to deduce this using the Laplace transform with zero initial conditions. So you compute the transfer function from U to Y. Okay? In this case, C, well, C is just row vector C1, Cn. This is a scalar system. Now, A is this lambda, is a diagonal of numbers, lambda 1, lambda n. If you compute the Si minus A, then you get S minus lambda 1, S minus lambda 2, etc. in the diagonal. The rest is 0. And the inverse is just the inverse of the elements in the diagonal. And then you multiply by B, which is just something. Now, if you do these computations here, you get a summation of terms that are Ci bi divided by S minus lambda I. And in general, you have n terms, okay? Where n is the order of the system, is the dimension of the state. So in general, the transfer function will have the order of, or the dimension of the state. The order of the transfer function is the dimension of the state. But it can be smaller. Suppose that some of the C's or some of the B's are 0. Then the corresponding term collapses and you will have, you are summing over less than n terms. So the transfer function will have order smaller than n. Or suppose that you have repeated lambdas. In that case, again, some terms can be added up. And the order is smaller than n. Okay, so the transfer function will have an order which is smaller than the dimension of the state when either C equal to 0, B equal to 0, Ci equal to 0, Bi equal to 0, or lambda I, or you have lambda I repeated. But these are the conditions for the system to be both controllable and observable. Remember that controllability condition was all the Bi's different from 0, no repeated lambdas. Observability conditions, all the CI different from 0, and no repeated lambdas. In other words, if your system is controllable and observable, the order of your transfer function is maximum and is equal to the dimension of the state. Okay? If instead you lose controllability or observability, your order will be smaller. This means that there are some of these poles that are cancelled with zeros. The zeros do not appear here because I'm summing these terms constant divided by s minus lambda. But when I do the sum and I reduce these to a transfer function to a common denominator, which is s minus lambda 1, s minus lambda 2, etc., then I will have also zeros. And if I have pole zero cancellation, then the order will be not n, will be smaller because some of the poles will be cancelled. And in that case, I'm losing controllability or observability. I don't know which one, but one of them is for sure lost. Okay. So pole zero cancellation is in the transfer function corresponds in the state space with loss of either controllability or observability. Now we have shown this feature in the diagonal, in the case of a diagonal system, but it is a general situation. So you can prove in general that if you don't have any pole zero cancellation, then you will have a transfer function for which the order is equal to the dimension of the state. Okay. And if, for instance, you want to design an example in which you have a pair AB which is not controllable or which is not observable, what you do is you start with a transfer function for which you have a pole zero cancellation, and then you do a state realization for that using the techniques that we have studied to obtain the state model from the transfer function. Questions about this? So this is an important conclusion that you should remember, which means that if you lose controllability or observability, then there will be pole zero cancellations. Okay, and this is a general fact for not only for the diagonal systems. Let's see some examples. Okay, before the examples, actually, if you have a general system of order n, you can do a state transformation, a coordinates transformation, so that the state changes and the equations change, and you end up with a new state for which you have this structure. You have one part which is observable and controllable that connects the input with the output. You have one part which is not observable but controllable. This part is affected by the input but does not affect the output. Another part which is observable because it affects the output but not controllable because U does not affect it. And one part which is not controllable, neither observable. Of course, you can have systems in which everything is observable and controllable, nothing is observable, neither controllable, and so on. So the four blocks need not appear in all systems, but in general, these are the four possibilities that appear. Okay, and the transfer function depends only on the block which is observable and controllable. So it corresponds just to this A11 block here. Okay, this is the so-called Kalman decomposition. We are not going to use this much or probably at all, but it's interesting to make this remark. Okay. One remark, again, this is something that we are not going to use much in the course, but you might read some book or some paper, in particular when you will be doing your thesis, and it's a notion of reconstructability and detectability. Okay, so we say that state realization AC is observable if you observe the output for a finite period of time and you recover the initial condition. If you are able to reconstruct the final state xt, then you say that the realization is reconstructible. You can reconstruct xt. Okay. Now, in continuous time, observability and reconstructability, they are equivalent. So if you are able to estimate the initial condition, you can estimate the least observed point of the state, xt, and vice versa. If you observe xt, so the system is reconstructible, you are able to compute also x0. Okay, so in continuous time, this is equivalent. But in discrete time, this is not equivalent, because remember, in continuous time, there are plants for which you cannot go backwards. The other notion is detectability. Okay? And we say that the system is detectable if the parts of the state that are not observable are asymptotically stable. Okay? This, in practice, this is important, because if you know that your system is detectable, you can only stabilize part of the state, but the part that you cannot stabilize because you cannot measure, you know that they go to zero by themselves. So this is the notion of detectability. Okay, so these are complicated names in the first approach. Don't bother too much with them. Little by little, you will get acquainted to it. So let's see one example. Now, I would like you to invite, the solution is in the next slides, but maybe you can try to do it by yourselves in your notebook. So write the state equations for this system. Alpha is a parameter. Okay, so remember, alpha can be, say, 2, 5, minus 5, minus 3, whatever number you want to place. And you have these two state variables, x1 is equal to y, and x2 is equal to the output of this system, of this block. Okay, so write the state equations, and now find for what values of alpha is this system controllable, and for what values of alpha is this system, is your state realization observable. Okay, and then give an interpretation in terms of a transfer function. That is to say, when you lose controllability or of observability, you will have a pole zero transform. Understood? Everybody understands the problem? So start, don't look at the solution, because if you look at the solution, you will learn nothing. Let me just copy. will go to the whiteboard, but I will redraw this in the whiteboard. Please raise your hands when you have the state model. Write x2 in the S domain and then go back to the time domain. And x2 is a transfer function alpha minus 1 divided by s plus 1 multiplying u of s. U. So this is s x2 plus x2 equals to alpha minus 1 u. So you end up with x2 dot equals to
equals to minus x2 plus a minus 1 times u.
good. So let's write. Everybody understands this? This is one of the state equations. Where is it? Here, and this is the other state equation. So let's write here x1 dot x2 dot is equal to x1 x2 plus this multiplies u. And what I have here?
0.
0. Here,
1,
1.
0, -1.
Alpha -1. Okay, you will have to know some Greek. So this is the first letter of the Greek alphabet. You read it alpha. Alpha. Okay? And the output equation is what?
1, 0.
1, 0. Good. Can I clean this stuff here? Or anyone wants to make some question? Alguém quer fazer uma pergunta ou posso apagar? You won't be able to succeed in ending this course if you are not able to do this. So if you have any doubt, tell me right now. Okay. Now, controllability matrix is B and AB. And this is what? B is 1, alpha -1. What about AB?
Alpha -1.
1 minus
minus
alpha.
Now, one question is, for what values of alpha is this controllable? What can we do? The rank should be 2, no? Because this is a 2 by 2 system, or the determinant of C should be different from 0. So you lose controllability, lose controllability for determinant C of C equal to 0. So this is, what is the condition? 1 minus alpha minus alpha minus 1 squared. Okay, equal to 0. So you can solve this, no? This is 1 minus alpha squared minus 2 alpha plus 1, and you get what? If you equate to 0, multiply everything by -1.
Professor, isn't it plus 2 alpha because of the minus before the...
That's right. And this is -1. That's why I'm always asking for your help, and you don't help me, and you do such a foolish thing. So this is the one that should be. Good. So this cuts with that one. And I have alpha, 1 alpha, I multiply everything by minus alpha 1 alpha plus, oh, that should be a minus. Okay, so this is alpha minus alpha squared. So alpha minus alpha squared. So what are the values of alpha that leads to a loss of controllability? It's alpha
0 and 1.
and alpha equal to 1. So in this case, you can give at least in one of the cases, you can give one simple interpretation. What happens if alpha is, can you give a, right now, without making anything, saying that, of course, for that value, the system becomes not controllable. In terms of the block diagram.
If alpha is 1, then the whole block disappears. If it's 0, then it cancels with the pole.
That's right. That's right. If alpha is 1, it's obvious that x2 is not affected by u. Okay. And now let's do the transfer function. So what is a transfer function? You have 1 plus alpha minus 1 divided by s plus alpha multiplying by 1 divided by s. And this is what? S plus alpha, s plus alpha, plus alpha, so the 2 alpha minus s divided by s plus alpha s. So there must be something wrong here. Alpha menos 1, s mais alpha mais alpha menos s. Tem para aqui um erro, não é? Alguns, não é que eu tenho um erro. Oh, this is not alpha, this is 1.
And in the top part of the quotient is in.
This is 1. This is 1.
Yes, yes.
Not s. So this is 1. Thank you. Okay. There must be still something wrong.
Yes, the last equation.
Here. S
Yes, yes.
plus 1. Oh, let me.
The one
Clear.
cancels and stays only s plus alpha.
So s plus 1 minus 1, s plus alpha. Right? Now I think it's correct. Okay? So what happens if alpha is 0? If alpha is 0, you cancel s with s. This is an s. Okay, so we have a 0 cancellation. If alpha is 1, you also have a 0 cancellation. So alpha equal to 1 on one side is obvious because it blocks, but it also has a pole 0 cancellation. Okay?
Professor,
Yes, yes, yes.
can you please explain how, I understood everything, but can you explain how we got the matrix 1, alpha minus 1, alpha minus 1, 1 minus alpha?
You mean the controllability matrix?
Yes, please.
Okay, we have, I have stated before that for a state realization to be controllable, this matrix must have rank n. So in general, you have a matrix, I call it controllability matrix, is B, then AB, then A squared B, up to A, and minus 1B. Okay? Now, in this case, the system is of order 2. So n is 2, so n minus 1 is 1. So you stop at AB. You just have the first two terms. And the rank of this matrix must be equal to n. That is to say, in the input-output case, in the single input, single output case, this matrix is squared, so you can just compute the determinant. Is it clear now?
Yes, but I don't get how did we define the 1, alpha minus 1, alpha minus 1?
You don't get what?
How we got these values? Like I understand the
You
range.
mean where does this comes from?
No, under it, just under it.
Here.
Yeah, yeah.
Well,
This
B,
no,
B.
just after this, on the right. Yeah.
AB.
Yeah. The
So
matrix.
multiply A by B. So 0 times 1, 1
Okay, understood.
alpha minus 1. Okay, so that's alpha minus. So it's just matrix multiplication.
Yes. Okay.
Okay.
But Professor, just one question too. If the A matrix was 3 by 3, for example, we would go to, it would be B, AB, and A squared B?
That's right.
Okay.
Correct.
Thank you. Okay.
Okay. In the exam, I will place a problem with n equal to 5. So no, for sure, not for sure. Okay. In MATLAB, you have there is a function that allows you to compute the observability matrix. If you give me one moment, I will tell you which one. Because sometimes you need it in practice. OBSV. So OBSV is a function that allow you to compute the observability matrix in the okay, this is for the observability. For the controllability, this is the controllability matrix. For controllability,
I think for controllability is STRB. CTRB.
probably yes. Just let me check. CTRB. That's right. So CTRB. Okay. Any more questions about this problem? Now, what about observability? In observability, can I clean this stuff here? Okay, for observability, you have to compute.
Professor, just one quick question. Why did you write that OPS observability and control.
So OBSV and CTRB, they are MATLAB functions.
Ah, okay, okay, okay.
And you
okay.
can compute the observability and controllability metrics numerically
Okay, okay,
with MATLAB.
okay,
These are MATLAB functions.
okay. Thank you.
So I have a small booklet where I take note of these MATLAB functions or tricks, or so probably should do the same. Okay. So for controllability, what is the controllability matrix? You remember? So the observability matrix. Oh, it's O of AC. It's C. Then CA. Then it would continue to be CA squared and so on. But we have n equal to 2, so we just have this. So this is 1, 0. And CA multiplies CA, so CA, that's 0. And CA, that's 1. So do you have problems with alpha? With the alpha, is alpha able to destroy your observability?
No.
No, because what is the rank of the observability matrix? The rank is the number of
2.
independent lines or columns. Yes?
2.
2. You have obviously 2 independent. The two lines are independent now. Okay. This first line is 1, 0. The second vector is 0, 1. So they are linearly independent. They point in completely different directions. Okay. Now, if you want to do another exercise that I shall not do here, repeat this problem, but now interchange the blocks. So do something like this. And this is x2. And this is y. And you add. Okay? So solve this at home. If you don't want to solve it at home, go to Poline or to some nice open air place and solve it. You can also, it's even nicer. Okay? Any question? So let's go back to the slides. There is another exercise here. Okay, this is what we have been solving. This is a little bit more complicated exercise. I won't do it here. You can use it when you study the slides. Okay, so up to now, today we introduced the concept of observability. Then we have learned that when you have pole zero cancellation, if you lose observability or controllability, you will have them for sure. So pole zero cancellation implies either loss of controllability or loss of observability or loss of both. Okay, you don't know which one will happen. Now, this is an important structural property. Now let's speak about linear state feedback. Okay, and what is the problem? What is the problem that we have here? Suppose that I give you a plant and you know a state realization for that plant. Okay, typically you are a process engineer, you get data from the plant and you identify this data and you find out A, B, and C. Okay, and now you want to design a controller. And let's assume that the characteristic polynomial of the matrix A, I call it AS. So AS is Sn plus A1, Sn minus 1, etc. up to An. So that's the notation that I'm going to use. And this is the determinant of Si minus A. That's the open loop characteristic polynomial without any control. Now, assume that you measure the state. Later, we are going to see what happens when you are not able to measure the state. But for the moment, assume that you measure the state. And your admissible control law is a reference minus a vector times x. Well, this vector, if u is a scalar, this vector must be of what dimension? Row or column?
Column?
No, row, because if you have x is a column, so you multiply a row by a column to get a scalar. So it's a row. It's a row.
Oh, okay.
Okay. Now, my problem is, well, don't forget too much about this R. Okay, so this R, think of them as 0 for the moment. It's the reference, and later we are going to see how we can deal with this R. So think that it is there, but it's 0. So you just do a state feedback, and your problem is to stabilize the system. So imagine that your system is not stable and you want to stabilize it. So you want to impose the closed loop poles. So the closed loop poles are obtained by forcing you to be R minus Kx. So you plug it there, okay? And instead of imposing the closed loop eigenvalues or the closed loop poles, you select a polynomial with the poles that you want to impose. So this alpha polynomial that you see here in the bottom is such that its roots are the poles that you want to impose to the closed loop. Let's see a block diagram. So you have your plant, okay? This dotted square represents your plant. And your model for your plant is the state model. Now you assume you measure the state and you do a feedback of the state. So inside the dotted square, this is a physical system that you have. And you have some sensors here. You measure all the state with sensors, and then you do a linear combination. When you write Kx, you are doing nothing more than a linear combination of the different states. K1x1 plus K2x2 and so on. Okay? And you put a minus sign and you reject it. Okay? You place that DR because later the reference will appear. Now, why do you place this minus here? Well, it's immaterial because if you had not placed the minus, then the sign of the coefficients of K would be changed. But for, let's say, for historical reasons, we put a minus here to remember that we are doing a negative feedback. Okay? Now, when you force this controller, okay, and remember this K is in your computer, and the dotted block is the physical plant, okay, and everything together works according to these two equations. So if you want to have an equation for the closed loop, what you have, you just plug this there, so you get AX plus BR minus BK X, and you collect the terms in X and you get this equation. Is it obvious to everybody that this last equation is equivalent to this, to the coupling of the previous two equations, eliminating the U? Everybody agrees? No questions? Okay. So this model here is now the model for the closed loop. And as you see immediately something which is quite remarkable, is that the dynamics matrix is no longer A, but is A minus BK. So by changing the K, you are able to place the eigenvalues in different places. Okay, you are able to affect the matrix of the dynamics, so the eigenvalues will be different. So what are we going to do? We find this closed loop matrix and we write its corresponding characteristic polynomial. So I call it AK to remember that it depends on the vector of feedback gains. Okay, it's determinant of SI minus A minus BK, so minus A plus BK. Okay, that's this matrix here, A minus BK. You get SI minus A minus BK, that's minus minus gives you plus BK. Okay, and this is a polynomial, and I can adjust, it's a polynomial in S, and I can adjust the coefficients of these polynomials by the choice of K. Now, I want to adjust the coefficients such that this polynomial, this closed loop polynomial, is equal to the desired or specified characteristic polynomial. So I want to solve this equation with respect to K. Okay? And for that, one possibility is to find K such that the corresponding coefficients of alpha K and alpha, AK and alpha match. So I'm going to equate A1K to alpha 1, A2K to alpha 2, etc., ANK to alpha n. And I get a system of equations. Remember that these coefficients depend on K. Okay? Now, if the pair AB is controllable, in the sense that we have just studied, this system of equations always has a solution, no matter what the value of alpha that you have specified. That is to say, if the pair AB is controllable, you can place the poles of the closed loop where you want. Now, how can I solve this problem? How can I solve this problem? I will give you one solution here, and we have seen one example. Let's go back to the very beginning to remember some slides. Remember, suppose that I want to impose the poles of the double integrator, and I do a feedback of these states. Okay, so what I do is I compute, this is my alpha K, This is my alpha k here. And I equate it with this, sorry, that's my AK, and I equate it with alpha. So I want that the coefficients of my AK here in the second line are equal to the alpha. The alpha polynomial is a polynomial with roots at -1 plus or minus j. Okay, so I equate the coefficients of the polynomial, and I get equations for the gains. Here I had that story of the common gain k. That's why there appears here a product of gains. But in general, I'm going to end up with a linear system of equations. So this is the method of unknown multipliers. Later we will see. Next Tuesday we are going to do some examples so that you can check it. But let me introduce you for the moment. Let me introduce you a formula that you can use. And this is the Bhaskara formula. Okay, looks quite cryptic. So the vector of gains is, you see this alpha, when I write alpha of S is the polynomial alpha of S. But when I write just alpha, is a vector of the parameters. You understand the difference? So alpha denotes the vector of the parameters of the polynomial. Alpha of S means Sn plus alpha 1 Sn minus 1 plus alpha 2 Sn minus 2, etc. So alpha is the vector of the coefficients of the polynomial that I specified to be the closed loop polynomial. A is the vector of the parameters of the open loop polynomial, something that if I know the initial model, I can compute very easily. And then M is this matrix here. Okay? And then I do this, and this C is the controllability matrix associated to the pair AB. This looks quite cryptic, isn't it? But we are later, next Tuesday, we are going to prove this formula. And you are going to see that the concepts that we studied before fit together in a very simple way to get this formula. It's not so difficult to get it. Today, I just want to do one thing, which is to give you an example. Now, suppose that we have the previous example. Okay, now I put here a 2. And I want the closed loop poles at -1 plus or minus j. Now, what shall I do? First, I write the equation. So remember that where is x1 dot? This is an integrator. So here you have x1 dot equals to x2. x2 dot equals to 2u. These two equations that I write in matrix form. So I have my A matrix and my B matrix. Then I compute the controllability matrix B, AB. This is a second order system, so I stop here. And just B, and I do the product AB, and I get it. Now I invert it, okay? You have to know how to invert matrices. Now, compute the characteristic polynomial of A. So you just pick up the open loop matrix A and compute the determinant of Si minus A. And you get S squared, which is something that you should expect because you know that the system is a double integrator. So both poles are at the origin. Both the open loop poles are at the origin. Now, A of S is according to our notation, S squared plus A1S plus A2 in this second order case. And A1 is 0 because this is just S squared, and A2 is 0. So compare it with A. So according to our notation, A1 and A2 are 0, and A is 0 because A is A1 and A2. Now, M is this M, so it's a lower triangular matrix. This is zeros. I have ones that are diagonal, and then I have a 1, a 2, etc., up to n order n minus 1. So in this case, the order is 2, so n minus 1 is 1. So I just put here a 1, which is 0. And the inverse is very simple because you just invert it and transpose it. It's diagonal. A diagonal, it's an identity. So the transpose of the identity is the identity. The inverse is still the identity. So it's very simple. Now, what is the desired characteristic polynomial? Is something that has poles at minus 1 plus or minus j. So remember that how can I find these poles? How can I find these poles? So if I want to find poles at P1 and P2, my alpha of S is S minus P1, S minus P2. Okay? Now, if P1 to a trick is so gamma plus or minus J delta, then your alpha of S is S minus gamma squared plus delta squared. You see why? Because if you make S, say, equals to gamma plus JS, then plug it there, is gamma plus JS minus gamma squared plus delta squared. So this cuts with this, and you get JS squared, which is, what is JS squared? JS squared. What is this?
Minus S squared.
Minus S squared, no? So it's J squared, S squared, J squared is minus 1. So you get, oh, sorry, this is not S, this is delta. No? You get minus delta squared plus delta squared, which is 0, okay? This is delta. S equals to gamma J delta. Okay, so I put the J delta there. Okay, so this is a useful trick. Remember, when you have complex conjugate poles, the way to write a polynomial, then this is easy to expand. So S minus the real part plus the imaginary part squared. S minus the real part squared plus the imaginary part. If you don't remember this, okay, in general, if you want to have two poles P1 and P2, S minus P1 times S minus P2, okay? That's the way of getting the alpha. So I should find out what are the convenient poles, and we can discuss it later. This is the engineering problem is finding the convenient poles. Then the rest is the mathematical problem. Okay, so just to conclude, the example, now I have everything. I have alpha, so and the coefficients alpha 1 and alpha 2 are 2 and 2. So I have alpha minus a, this is the formula, no? Alpha minus a, 2, 2, that's the coefficients of alpha, 0, 0, the coefficients of a, subtracted, m minus 1 transposed, which is the identity, times the controllability matrix, which was this one. Okay, and if you do all these computations, you get k equal to 1, 1 by magic. Okay, so this is how to use the formula. Now, we have a number of things to explore. One is where does the formula comes, and this is something that we are going to see later. Another thing is, in some cases, to have some proficiency, not instead of using the formula, using the so-called method of unknown multipliers, the first example that I gave. Any question? Okay, if not, we stop here.